Good afternoon. Welcome to NASA headquarters. Today we'll give you an overview of the Voyager mission, highlighting recent analysis, and of course presenting pictures taken of our solar system. To do this, we have Dr. Ed Stone, Voyager project scientist from the California Institute of Technology. Later we'll have remarks from Dr. Carl Sagan, professor of astronomy and space sciences at Cornell University and a member of the Voyager imaging team. And to help field any questions you may have at the end of the briefing, we have Mr. Joseph Alexander, Assistant Associate Administrator for NASA's Office of Space Science and Applications. Just want to make sure that you know that at the end of the briefing, a package of photos will be distributed. They're being compiled right now, as well as a clip of the proceedings. Thank you. Dr. Stone?
Good afternoon. Well, today marks yet another milestone in Voyager's exploration of the solar system, the completion of mankind's first picture of the solar system from beyond the outermost known planet. And although this will be Voyager's last images of the planets, they also mark, this image also marks a new phase in the Voyager investigations, the comparative studies of the diverse and distinctive worlds that Voyager has revealed to us over the last decade. So we felt it would be appropriate as part of this, of releasing the picture of the solar system, to describe some of what we've begun to understand by comparing what we've learned among the planets. And in particular, I'm going to focus on some areas where we've completed some recent analysis. So if I could really go to the first slide. Again, I always like to start with the basics, to remind everyone of the planets in the solar system, the fact that near the sun are the small terrestrial bodies, rocky objects like the Earth, at greater distance from the sun where it was cold enough that water could form into solid material, ice, and therefore be easily accreted to form the cores of the giant planets. We have the four giant planets, Jupiter, Saturn, Uranus, and Neptune, which Voyager set out to explore in 1977. And finally, still a third class, all by itself, a third class of planets, that is Pluto, of which we believe Triton is our best example that we've had a chance to look at up close. The next slide reminds you of the, if I could have the next slide, please, of the fact that there are two spacecraft were launched from Florida in 1977. Voyager 1 was on the faster trajectory, arriving at Jupiter in March of 1979, picking up a big boost in velocity because of Jupiter's orbital motion around the sun, acting like a slingshot, hurling Voyager on out to an encounter with Saturn in November of 1980. We had two key objectives at Saturn, which affected the trajectory. We wanted to fly behind the moon Titan, and I'll report briefly on what we learned from doing that, and we wanted to fly behind Saturn's rings so that we could probe Saturn's rings with the radio system. And I'll also report briefly on what we learned there. Those, since at that time the ring system was inclined and Titan's orbit was inclined, Voyager's trajectory ended up heading up out of the plane. Voyager 1 headed up out of the plane of the planets. Voyager 2 could have exactly repeated that experiment had Voyager 1 not completed those major objectives. Fortunately, it did, and we remained then in the plane of the ecliptic, flying by Saturn in such a way that we could head on to Uranus, and then just most recently, last August, past Neptune, completing what's called the Grand Tour, an alignment that happens once every 176 years. I should comment that this is not only a very interesting way of getting four planets, if you like, for the price of one, but in fact it was essential, because by using the boost that we picked up, the slingshot effect we picked up at each of our flybys of Jupiter, Saturn, and Uranus, it took us just 12 years to get to Neptune rather than 30 if we had launched directly, and if we'd had a large enough launch vehicle, which we did not have, to launch directly to Neptune. Next slide shows then the four giant planets and to scale an image of Earth to again illustrate that these are a giant class of planets. There in fact are two separate subclasses, Jupiter and Saturn, which are mainly hydrogen and helium, and at the center of them is indeed a core of material which was accreted or collected as comet-like material, but is now liquid, that is melted ice and rock. In the case of Uranus and Neptune, they have very much a similar core in their interior. They just have a much less deep atmosphere of hydrogen and helium, and they have an excess abundance of methane, natural gas in the top of their atmosphere, which absorbs preferentially in the red end of the spectrum, giving those two planets their characteristic blue color. One of the major objectives we had was to study the weather systems on these giant spheres of rotating gas and fluid. As far as we know, there are no solid surfaces at all. It's so hot in the interior. And of course, as we already knew from Jupiter, the weather systems, at least on Jupiter, the weather system looked quite different than that here on Earth. The next slide shows that besides discovering that the Great Red Spot itself is a giant hurricane-like storm system, some 3 Earth diameters across, and I'll show you some recently completed reanalysis of the images of the Great Red Spot. We found there were literally dozens of other storm systems, which again I'll describe in a few minutes in more detail. The next slide shows that one other key measurement that was made was the wind velocities, although ground-based data had provided a fair amount of detail on this already. That is that there is a strong eastward jet stream of about 200 miles per hour at the equator. Then there is a westward jet, an eastward jet, westward, eastward, and these opposing jet streams turn out to be a very important factor in creating the weather systems which we see. And I'll come back in a few moments to a recent model which has been developed using this exact wind profile to essentially demonstrate that I think we are beginning to understand why spots form and why there's a great red spot. Why there's a great spot, at least. We don't understand why it's red. I think now I'm ready for the video, please. We did at the time of the encounter with Jupiter, if I could have the video, please, the first video, number 3, that we did process the data at that time to look at the winds in the atmosphere. We've now reprocessed it using modern technology, which in fact, as you can see, produces a much clearer representation of this is actual data now, actual time-lapse photography showing the opposing jet streams. For instance, here you can see a westward jet stream and an eastward jet stream, and the large degree of turbulence which is generated at the interface between these opposing jet streams. This is now the Voyager 1, an enlargement of the Voyager 1 jet streams where you can see even more clearly. These are plumes, convective plumes. We believe they erupt at the head, at the small end of them, and the lower velocity at the higher altitude trails the ammonia ice crystals, which we believe is what the white material is, behind forming these long plume-like structures. Here comes the Great Red Spot into view now, and one will see that behind the Great Red Spot there is a large region of turbulence where the flow has been disturbed by being displaced or by the presence of the Great Red Spot itself, which acts like a very rigid cylindrical object in the stream. In this Voyager 1 image now, a set of images, time-lapse photography, you can see the small spots, the small storms. Each one of these is a small hurricane-like storm system. And if you watch this pair right here, you'll see suddenly they merge and become one. If we now look at the Great Red Spot, we find that these small storms also occasionally merge with the Great Red Spot, if you like, feed the Great Red Spot. Without a constant input of fresh storm vorticity, if you like, into the Great Red Spot, it indeed would slowly but surely contract. Again, you'll see another pair of spots combining to form a larger spot. Notice that these brown spots also have white clouds at their core. This is a comparison now of the nature of the Jovian atmosphere about 4 months apart. That is, this was March 1979, and this was 4 months later in July of 1979. So we have two snapshots, if you like, of the atmosphere, which show distinct differences. For instance, you can see there is a slight change in appearance in the Great Red Spot between Voyager 1 and Voyager 2. But more interestingly, it does appear that some of these small storm systems, which had been coming in and merging, seem to be deflected and, in fact, are essentially rejected by a pressure barrier which is here, and we have something what you might call a conveyor belt, where the storm systems come in and head back east without actually reaching, many of them reaching the Great Red Spot itself. That change in the atmosphere took place over that 4-month period, and of course one thing we hope that Galileo will do is provide us more continuous coverage of these changes in the complex dynamics. Now this is a model which Tim Dowling at Cornell, using Cornell supercomputer, and Andy Ingersoll at Caltech have developed, using that wind profile I showed you, putting it into a mathematical model, watching the shear between the velocity, the actual observed velocity, generate the turbulent storm systems, which then slowly but surely form into the circular hurricane-like structures. This is a mathematical model into which the velocity profile has been put, but the storms were not put. And out of that model comes the storms which you see, and you'll notice, in fact, just as in Jupiter, two smaller storms merge in this mathematical model to form a larger storm. The latitude at which these storms are forming is the latitude at which the Great Red Spot, in fact, is observed. And here is another merging, which you can see occurring. So in the basic vorticity, that is the polarity of the circulation, is counterclockwise in the southern hemisphere, as it is for the Great Red Spot. So I think that, and this model was actually published just last year in 1989. The problem was hard enough that it took basically 10 years for the scientists involved to be able to generate this kind of a model of the Great Red Spot. That's it for the video. Thank you. Saturn also had wind systems. This is a reasonably natural colored image of Saturn. It's not so brightly colored as Jupiter, nor is the contrast so great, but it certainly does have latitudinal markings, as one can see. And the next slide shows that not only does it have latitudinal markings, but in fact it also has storm systems which occur at where the jet streams oppose each other. It has a red spot, but not as large as the Great Red Spot. It's in the southern hemisphere, about 1/3 the size of Jupiter's Great Red Spot. So in many ways, Saturn, even though difficult to observe from Earth, has many of the same characteristics, but in less abundance, I think, than was the case at Jupiter. But there is less energy to drive weather systems at Saturn. Saturn's twice as far from the Sun. That means it has, on the average, about 1/4 as much energy per unit area to cause weather as does Jupiter. That meant that the velocity that was measured at Saturn, as shown in the next slide, was a surprise. Next slide. That is that the wind profile in Saturn shows the east-west jet stream structure, but the surprising thing was at the equator, the jet stream was almost 1,100 miles per hour eastward, much greater velocity than had been observed at Jupiter. So even though there was less energy, it appears, in fact, it turned out that Saturn had a higher velocity equatorial jet stream. The next slide shows Uranus, which is tipped on its side and has a rather different atmosphere, or it should have had, we thought, a different atmosphere, because over its year the polar regions receive on the average more sunlight than the equatorial region, unlike the other planets that we've been studying. Yet we found that the equator was just as warm as the polar region, but it was a very quiescent atmosphere. There were relatively few plumes. This small white feature you see here is one eruptive plume, perhaps like those abundance of plumes that we saw at Jupiter, allowing us to measure winds in Uranus's atmosphere, but Uranus turned out to have a rather quiescent atmosphere. Of course, it receives a great deal less heat yet to drive the weather system, only about 5% that which Jupiter receives from the Sun and from its internal heat source. Then it was on to Neptune, which has about the same amount of energy to drive its weather system. And having seen Uranus, we were therefore quite surprised to find that Neptune, with essentially the same amount of energy, nevertheless had a great spot, which was as large relative to the planet as the Great Red Spot is to Jupiter. And I'll show you some recent ideas about the nature of this spot. In addition, there was a smaller dark spot, as well as some other bright white clouds. In this case, the white clouds are thought to be frozen methane, frozen natural gas, while on Jupiter and Saturn, they're believed to be frozen ammonia. I think now it's, if I could have the I have the video, please. Let's look at now some of the atmospheric features on Neptune. This is a set of 5 images taken over one Neptune rotation. There is no motion within the image, just the rotation itself, which is done in the computer to allow one to see here's a small white cloud feature down near the South Pole, the small dark spot, and the white cirrus clouds, which one can see at these higher latitudes. Now, this is an indication of the relative motion, that the fact that here the equatorial velocity is westward, just the opposite of Jupiter and Saturn, and about 700 miles per hour. In other words, it's a stronger wind than on Jupiter, and in fact, we believe that's not the fastest wind on Neptune, and I'll show you in a few moments the evidence we have for still faster winds on Neptune, even though the amount of heat available is considerably less than on Jupiter. This is a computer graphic, now a computer representation of Voyager approaching the planet, showing the 4 rings which Voyager discovered, the ring arcs, which were imaged by Voyager, and some of the new moons, the 6 new moons, which Voyager discovered orbiting Neptune. Here is the great dark spot. There are 29 images taken over a period of several days. This is not the outline of the planet, but a small inset, if you like, a telescopic view. You can see that unlike the great red spot, which is a very rigid vortex, a very rigid storm system, this storm system is rather different. And you can also see that some of the white clouds appear to overtake and pass the great dark spot. Those clouds appear to be moving at something like 1,300 to 1,400 miles per hour. Now, it turns out in 1981, Kita did a calculation of exactly how vortices should behave in such fluids. And even though it's a very simple calculation, this is now a mathematical model. This is from a paper by Polvani, Wisdom, Ingersoll, and DeYoung, of what's called a Kita vortex. And you can see the remarkable similarity. And it turns out that the vortex, the outline of the vortex, is not really rotating, but it's just changing aspect and wobbling up and down. Although the interior fluid is indeed has an anti-clockwise motion, the boundary, in fact, is oscillating and not rotating at all. And you can see how similar it is to the behavior of the great dark spot. So in this case, it appears as though we have an explanation much more promptly. I think that's for the videos than we did for Jupiter, but partly because the theory actually was calculated for other reasons almost 10 years ago. Well, we did have some more Neptune. Yes, continue with the Neptune's crescent. This is another new set of images which have been prepared recently, and it's being introduced by essentially flying the Voyager spacecraft over an actual image of Neptune, but of course the rings are not actual images. Those are computer graphic representations. Onto the dark side, where, as it turns out, if there had been enough light, we would have seen the great dark spot, or if there had been enough Triton shine. Heading down south toward our encounter with Triton, we flew behind Triton to probe its atmosphere, just as we flew behind Titan at Saturn. And you'll see now the perspective that Voyager had of the Neptunian system as it left, and as it acquired images now of this lighted crescent, which we'll be seeing in a few minutes, the actual crescent that Voyager, a series of crescent images that Voyager took as it left the system. You can see this bright white cloud, which is at about 71 degrees south latitude. We'll see that in a moment now in an actual set of images. Here it comes. This is an actual set of images now. The South Pole, you can see by this small dark feature, which perhaps represents a polar vortex. You can see the small dark spot with its white cloud appearing, coming across the limb of the planet. Here is the bright white cloud, which is about 71 degrees south, that you can see moving with the planet. It turns out both these cloud features and the small dark spot are rotating at essentially the same rate, or very closely to the same rate as the interior of the planet. Unlike, now here is the cloud, which is at the center of the small dark spot. In fact, you could even see the shadow of the cloud on the deeper cloud deck. And finally, the lighted crescent of Triton crossing the dark disk of Neptune. All right, I think that's it for that video. Another area of research besides atmospheres was the magnetic fields of these giant planets. We already knew from Pioneer 10 flyby in 1973 and Pioneer 11 in 74 that a good deal about Jupiter's magnetic field, but there were some very major puzzles about that magnetic field. It turns out that the magnetic field extends something like 3, sometimes as much as 4 or 5 million miles actually from the planet. That was about 2.5 times larger. And in fact, one of the really surprises that Pioneer found as it approached Jupiter was that it met Jupiter's magnetic field 2.5 times further out than was expected. You can see relative to the size of the sun, these magnetic structures are immense structures. The next video now shows, no, the next video, please. If I could have a video, please. This is now a representation of what Voyager discovered was causing this inflation of Jupiter's magnetic field. This is the rotation axis, and you can see the axis of the magnetic field. This donut-shaped region represents the torus of sulfur and oxygen. About 1 to 2 tons of material per second are being stripped off of Io and carried into this donut-shaped region. And centrifugal effects spin that disk of heavy atoms and ions, heavy ions, far out into the magnetic field and stretch it out. And so this is the agent which inflates Jupiter's magnetic field to extend 2 to 3 times as far from the planet as it otherwise would. And you can see over the 10-hour period during which Jupiter rotates that this disk has a very ballerina skirt-like shape. This is something done by Ray Walker some years ago as part of the Galileo preparations, along with others at JPL and UCLA. Here is the solar wind, a 1,000,000-mile-per-hour wind, which in fact distorts the magnetic fields into these long tails. Voyager found the tail of Jupiter extended clear back to the orbit of Saturn, although, of course, it was quite fragmentary and not well organized at such a great distance. And here is Galileo, which will survey, that's it for that, which will survey the Jovian magnetic field for a period of several years, beginning in 1995. Well, Uranus held a big surprise for us. It was tipped on its side with its rotation axis pointed at the sun currently. We expected the magnetic poles would be near those same axes as they are on all the other planets we'd visited, and we found the magnetic poles instead to be down near the equator, tilted by a large angle and offset from the center by almost 1/3 of the radius of the planet. We initially thought that was an anomaly, that is, was an accident, was not of any fundamental interest, perhaps having to do necessarily of any fundamental interest, perhaps having to do with Neptune being tipped on its side and being heated more in the pole than the equator, or perhaps we were seeing the magnetic field reverse, as it does here on Earth every 500,000 years or so. Well, Neptune quickly disabused us of the fact that it was an accident, because Neptune also had a magnetic field which was tilted with respect to the rotation axis and with its magnetic poles much nearer its equator than near its rotational poles. And the next video now shows you the complexity that these tilted magnetic fields result in when you have a rotating planet. And with Jupiter, you saw the magnetic field just gracefully wobbling back and forth in the sort of an interesting dance. But in this case, we'll see in a moment in a model that was developed by Voigt of Rice University that the configuration is much more interesting in terms of its interaction with the supersonic solar wind, because it's tilted at this large angle, and of course the wind is then is incident on it, and the tail then is wound up like a very long helix as a result of this rotation of this offset and tilted magnetic field. So we now know, of course, that these magnetic fields are not accidents. The next slide, in fact, shows the interior are not accidents, but in fact have something to do with the flow of fluid, the currents in this ocean of water, which is probably ionized by the high temperatures and pressure, and somehow that flow tends to be concentrated in some way on one side of the planet, producing a magnetic field which is offset in the case of Neptune by about 6/10 of the planetary radius. Another area, next slide, of research had to do with the rings. And of course, Saturn's rings are the prototypical ring system, and until 1977 were the only known ring system. What Voyager discovered was the wealth and unexpected degree of detail which can be seen in this Voyager image. This is the A ring that can be seen from Earth, the Cassini division which can be seen from Earth, the B ring and the C ring all can be seen from Earth, but all the detail which appears here is not visible from Earth at all. And much of this detail in the B ring is still not understood and may well require the observations of the Cassini mission after the turn of the century to shed additional light on the nature of these features. The next slide shows the F ring, which orbits just outside the outer edge of the A ring. It cannot be seen from Earth at all. It was discovered by Pioneer 11 in 1979, 2 years after narrow rings had been observed or had been detected around Uranus by Earth-based astronomers. Because rings are made up of a countless number of particles in orbit around a planet, particles which collide with each other quite often, and collisions, of course, result in the loss of energy. And as everyone knows, when you have something in orbit around a planet and it loses energy, it spirals into the atmosphere. And hence one expected these rings to quickly dissipate unless something was constraining them. And in 1978, it was proposed that shepherding moons would be found just inside and just outside of these narrow rings. And indeed, that's what Voyager found in 1980, 2 shepherding moons, one orbiting inside and one outside of the F ring. So indeed, there is a mechanism, an observed mechanism for constraining material into narrow rings. Now, another thing which Voyager did, next slide, we also found, though, that the interaction between those satellites and the F ring was more complex than even the fairly complicated theory that explains shepherding, because the moons themselves are not in circular orbit, nor is the F ring, and one sees this kind of kinked kind of characteristic of the F ring and the multiple strands, which could well indicate that there are larger bodies which are a source of the finer dust material, which is in fact what's showing up so brightly in these images. Again, it will require a great deal more coverage of the Saturn ring system by missions such as Cassini to be able to sort out the complexity of the dynamics of these narrow rings. The next slide shows the A ring again. This is the Cassini division. All of these darker features on the A ring are now pretty well understood, and they're basically waves. They're very much like the wakes that trail a ship on in the surface of the ocean, except that in this case the ship is a satellite orbiting outside of the rings, creating by its gravitational influence a wake inside the rings, and because the satellite is in a circular orbit, the wave ends up generating a spiral density wave, not unlike in the very basic properties to the spiral density waves which may account for the spiral arms of galaxies. In any case, we use these spiral density waves, the characteristics of those waves, to determine how much icy material comprises the small snowballs and larger size, boulder size pieces of ice which make up the rings. And it turns out that if you could take all that material and compact it into a solid sheet of ice, it would be between 1 and 2 feet thick. We also use the radio system on the spacecraft, watching the radio beam propagate through the ring system. That provides information on the distribution of sizes of particles in the ring system. The next slide shows a computer representation. If this television screen, were 10 feet on a side, this is the distribution of particle sizes, although the particles themselves are almost surely not spherical, but irregular, icy objects, but the sizes would be as represented here. Mainly small particles with 1/8 as many for every factor of 2 increase in particle size. We headed on out to Uranus. The next slide shows some of the Uranus rings. There are 10 rings around Uranus. Voyager discovered 1 of them, and we discovered 2 of the shepherding moons which are there, but we did not find the others, presumably because they are too small to be seen and too dark. These rings and the moons themselves at Uranus are charcoal black and exceedingly difficult to image. The next slide shows the even more unusual situation at Neptune, where we indeed have, in this image, 2 rings. Actually, there are 3 rings as the computer graphics showed, plus a plateau of ring material. But this image shows the 3 ring arcs, which had been detected by Earth-based stellar occultations, in fact, did show up in these Voyager images. We have not found the shepherding satellites for Neptune's rings, nor have we found the mechanism which not only keeps the ring material from spreading out in radius, but keeps it from spreading out around the planet. So there is a major puzzle yet remaining in our understanding of ring systems. Next slide shows, though, that we now believe that we have evidence that the ring systems, in fact, are recent attributes of the planets. One of the key questions when Voyager started out its journey was, did the rings form at the time that the planet and all the satellites formed? It was just the material left over, if you like, which is orbiting too close to the planet to form a moon, or were the rings something which happened afterwards? We now believe, for instance, by measuring the details of Saturn's A ring and F ring and observing the motion of the shepherding satellites, which must move because they're the ones that keep the rings in place, that in fact the configuration of the ring today cannot persist more than several hundred million years. And so it appears as though rings, as we see them today, are not primordial objects at all, but are constantly evolving objects in the solar system, and are really the result, most likely, of the breakup of larger moons which were there at one time, and then the material continues to collide and generate the wide distribution of particle sizes which then are observed in the ring systems. Next slide, I think, takes us to the moons. Now, there are about 57 known moons in the outer solar system. That includes the moon of Pluto, so 56 around the planets that Voyager visited, many of which Voyager has discovered, most of which Voyager has shown us for the first time in any detail. Many of those moons are half water ice and half rock, objects such as we've never seen before. They don't exist in the inner solar system where it's much too warm. And it could have been, of course, that in fact many expected this is the kind of object we would see in the outer solar system. This happens to be the moon Mimas, one side of Mimas, heavily cratered by impacts, but otherwise not very remarkable. And I think there would have been a lot less scientific result from the Voyager mission and a lot less public interest in the Voyager mission had, in fact, the moons we observed all looked exactly like Mimas. Fortunately, nature presented us with a much more interesting solar system. Next slide. Actually, now I think I want to go to the video. No. Do I? Yes, right. This is the first moon that we took a picture of. This is not a Voyager image. This is a peak-to-me image, but this is now a Voyager image. You might say, when did we take that? We took that from the JPL parking lot 2 years before launch. And it was a demonstration of the basic sensitivity of the camera system. The natural color of the moon has very little color in it, but in fact, even a few % difference in color can easily bring out differences in the titanium oxides and iron oxides in the lunar maria. And so this was our first demonstration that this camera system, which takes a lunar picture of our own moon, which has a few % color contrast, would indeed be capable of looking at icy objects, which to first order are snow white, and being able to see some definition of contrast in even snowy white objects. Here's what the moon actually looks like, hardly any color at all. So we were quite encouraged that we would have a useful camera system for studying the moons of the outer solar system. If I could now have the next slide, please. Well, one of our first surprises was the moon Ganymede. Ganymede is actually larger than the planet Mercury. It was the first body, that and Callisto were the first such planet-sized bodies that we had seen up close in the solar system, which are half water ice and half rock. And it's the first, and it provided us with the first evidence that there is tectonic activity, that there is other than just impact cratering, which in fact has shaped the appearance and the structure of these icy moons in the outer solar system. The diameter of Ganymede is about 3,300 miles across, just slightly larger than Mercury itself. And if we could now take the next slide and show you that here this darker material is believed to be the older crust. It is separated by lighter regions, which I hope you can see are grooved. That is, this is called the grooved terrain, which is presumably a result of tectonic activity, that is, splitting off of slivers of material, of ice, and possibly then flooding by water coming from the interior. The impact craters, of course, produce beautifully white patterns by splashing fresh snow up on the surface of the planet, of the satellite. The next slide, the next view, the video, and I'm sorry, I want to go to the video now, please. This is now a recent set of images where the relief that's shown is actually derived directly from the data. This is you can now see the parallel groove terrain here, the characteristic scale being several kilometers, the height being less than a kilometer, maybe a few hundred meters, which is the result of this tectonic activity. You can see some of the craters have central peaks to them. There's been some rebound to these craters, but that this particular area that's in this particular flyover is an area where the surface has been renewed, if you like, by this tectonic activity. If I could now have, yes. Now, Enceladus is at Saturn, and here's Enceladus. It's a much smaller object. It's only 300 miles across, about 1/10 the size. We certainly were surprised to find that it too had tectonic activity on it, because normally tectonic activity is something you associate has to have heat. The larger the body, the more effective the radioactive decay is in keeping the interior warm. And here's a little tiny moon, which must have cooled off very quickly if nothing else had happened to it, and yet shows a great degree of tectonic activity, and also some areas which are heavily cratered. So this seems to have had a long period of tectonic activity, unlike Ganymede, where we believe the tectonic activity occurred in the first 500 million years or so. Perhaps this extended over a longer period of time, as can be seen now. In fact, if we look at, we now have another video which takes us over this very heavily cratered terrain, now this color is not really too bad. That is, this is a snow-white object. The reflectivity is almost unity for Enceladus. It's a very bright object. Here is a crater with a rebound peak in it, which suggests the material was soft enough at the time for such a peak to form. You now see these craters are cut in half by the fault systems which generated this groove terrain, indicating that the faulting occurred over a period of time after the intense bombardment. Okay, that's it for that video. Then we went on out to Uranus, to another small moon, also only about 300 miles across, and found an even more elaborate surface. And we now believe that, in fact, in the case of both Enceladus and Miranda, that there had to be some other source of heat besides radioactivity. And the thing which is suggested is tidal heating. That is that the moon is in orbit around the planet, but not in a circular orbit, and as a result, the tides, the stress, its surface is flexed as it orbits the planet, much as Io is still being flexed today as it orbits Jupiter, and that flexing has contributed to the source of heat, which then allowed these two small worlds to have this extensive kind of activity where major pieces of the surface have fault systems. The next slide shows this area up close, where you can now see parallel what look like scarps and many fault systems. And even down here, where if we take in the next image, one takes this same scarp and turns it around so that one gets a better sense, this scarp which is some 12 miles high. This is on a moon which is a mere 300 miles across. That was, even with all of our experience at Jupiter and Saturn, this still was a surprise to find such diversity on such a small world. Well, we had one more icy world to go beyond Uranus that we were going to visit up close, and that was Triton. If I get the Triton at Neptune. This is a Voyager image of Neptune and Triton from Earth. Of course, it's a point of light, as it is in this early Voyager image. It's in a retrograde orbit. That means it orbits Neptune backwards relative to Neptune's rotation. It's the only major moon of a planet which does that, and certainly suggests that it's most likely an object that formed elsewhere in the outer solar system, perhaps an object, a sister to Pluto, which was then captured and by Neptune and has remained in orbit, but has, as a result, suffered a very unusual thermal history, again associated with tidal heating. The next video now, its temperature of the surface is the coldest in the solar system, 390 degrees Fahrenheit below zero. Again, you see the long fault systems with ice which has extruded through the faults. Large, what look like lake-like frozen lakes of material which has come out in caldera that look a lot like volcanic caldera here on Earth. A nitrogen ice cap in its polar region and methane ice. Here's a long fault system, as you can see, again coming out from the polar region. And a very unusual feature which we don't understand. And in this perspective view, you can see, again, relief derived from the data indicating the rim of that impact crater. Is that it for the video? Here, oh, I'm sorry. No, it's not, because in fact the other thing we discovered that even at 390 degrees Fahrenheit, minus 390 degrees Fahrenheit, there is thermal activity today. This is a plume. It's not changing in altitude. It's because the spacecraft was changing perspective in these three images taken over several hours. One can see a plume extending some 5 miles up into the tenuous nitrogen atmosphere, presumably the result of a slight heating by sunlight of the nitrogen ice which is there. Well, as a result, Triton at Neptune did have an atmosphere about 15 millionths of the Earth's atmosphere, mainly nitrogen. It was Titan at Saturn, though, which had the really massive atmosphere. We didn't know how massive it was. There were suggestions it could be much less than the Earth's atmosphere in density, or it could be much greater. As it turned out, Voyager discovered that it is indeed 1.5 times the surface pressure of the atmosphere on Earth. It's mainly a nitrogen atmosphere, and the surface is completely shielded by a high-altitude haze, which is created by the action of sunlight, converting the methane, the few percent methane which is in that atmosphere, into complex organic materials, some of which remain suspended, blocking the view, others of which slowly but surely precipitate to the surface. Next slide shows a false color image of some of these haze layers, which are various different organic constituents to which we do not currently have any direct identification, but which can come from the whole chemistry can certainly be explored by the Cassini probe, which would be inserted into Titan's atmosphere after the turn of the century. The next slide, in fact, shows a cross-section of what that atmosphere looks like as far as Voyager knows, a surface which is at about minus 290 degrees Fahrenheit, very near the melting point of methane. Methane is not frozen on the surface. There is likely, according to theoretical models, a lake of liquid ethane, which is created out of the methane in the atmosphere by photochemistry and which then rains down on the surface. And there are these thick photochemical hazes which block the view. And it's this atmosphere into which the Cassini probe will enter and provide us direct indication of the complex chemistry that's occurring there today, and which may be related in some detail to the chemistry which occurred in the early Earth's atmosphere before life evolved. Well, I've left to last the most surprising of the moons that we discovered, that we have visited, and that was Io. Of course, now it's well known that Io was the second object in the solar system which had volcanoes, known to have volcanoes after the Earth, that this is a large deposit of a volcano, that this is a lake of liquid sulfur. The next, in fact, I think we see this region up close. You can see this is about 100 miles across. It's believed that that dark area is in fact a crusted over lake of sulfur. Its temperature is above room temperature, even though the surface temperature on Io is some minus 225 degrees Fahrenheit. The temperature of this little lake is near 100 degrees Fahrenheit, kept warm by the tidal flexing of Io's crust as it orbits Jupiter. And in this slide, one sees one of the many active plumes which were discovered by Voyager in 1979, Voyager 1 and Voyager 2. If I can now go to the video. This is recent reanalysis of the data from 10 years ago using modern techniques for display. You can see here's Prometheus, the deposit ring from Prometheus. This is Pele. We'll see it in more detail here. That's the Loki. And we'll now be seeing in a moment a movie that we took with Voyager 2. This is an actual movie. This is not a computer graphic showing the Maui plume and the plume Amirani. It's a period of about 3 hours of this movie, which was taken on Voyager 2, put in especially into the sequence after the discovery on Voyager 1, and now is available for further detailed study of the dynamics of these plumes of, in that case, sulfur dioxide. Now, this is the region near Pele where we believe the plume is driven by sulfur rather than sulfur dioxide because it's a much higher plume. This plume extending well over 100 miles up. And you can see the complexity of the scarps in the surface of Io. We believe that the underlying structure is silicate, but that it's coated with this is the plume now. This is the Pele plume in this Voyager mosaic. Is covered by sulfur and sulfur dioxide. So these are the 4 planets that Voyager has visited over the last 12 years. And all their many moons, their rings, all 4 have rings, all are different and diverse. But the Voyager exploration is not over. And the next, as the next image shows, the sun has a solar wind blowing radially outward from it at 1,000,000 miles per hour. The space between the stars, interstellar space, is filled with a very dilute gas, an ionized gas called the interstellar medium, and each star blows a bubble in that gas. We don't know how large the sun's bubble is, the heliopause. The distance from the sun out to the boundary of the heliosphere, the heliopause, the boundary of this bubble, may be 100 times as far as it is, 100 times as far as it is from the Earth to the sun. No one knows. But I can tell you that Voyager 1 and Voyager 2 have enough power on them to, if nothing breaks, and that's a big if, to keep returning data for another 25 years, at which point Voyager 1 will be 130 times as far from the sun as the Earth and could well be returning data from interstellar space for the first time. So there's still a number of important discoveries ahead for Voyager. But we took one last look at the solar system before we turned our attention to interstellar space. The next image shows where Voyager 1 was last February. Now, starting in 1981, in fact, Carl Sagan had urged the project to start looking at the Earth, using Voyager to look back toward the Earth. And over the various years, as Voyager 1 and 2 moved further and further out in the solar system, the idea of taking a picture looking back became more and more discussed and more comprehensive, because the further out we got, the more planets we were going to be looking back at. And until, of course, this last February, when Voyager 1 was outside of all the planets looking back, it became possible to take mankind's first picture of the solar system. And so this is a different kind of milestone than the scientific milestones we've had, one that is really symbolic of our increasing ability to explore the solar system. And it's interesting, I think, that the picture I'm going to be showing you next is not only the first such picture that has been taken, but in fact is the only such picture that is likely to be taken for the next several decades, because future planetary missions will go into orbit around a planet and will not have this unique perspective of looking from the outside back into our solar system. So if we now run the last video, please. Here is this. These represent the outlines of the 39 wide field fields of view, wide field camera fields of view, starting with Neptune, Uranus, and Saturn, and moving on in. We'll now show you in more detail. This is the Sun. This is Venus. That small point of light, of course, because from out there, the planets are small points of light. Here is the Earth. That tiny little dot is the Earth. The bright streak that was behind it was scattered light in the camera system. This is a Voyager image of Earth and Moon taken just after launch in 1978, as I recall. The next, in this brief tour of this picture of the solar system. The next image that will show up is the one of Jupiter. There's Jupiter. It was several pixels across, and of course here is the Jupiter as Voyager saw it when it was much closer than it is now. The next part of the sequence, and there's the great red spot that we've talked about this afternoon, and one of the dark barges that I did not discuss, but is another large storm system of still a different character. This is now, at this position is where Saturn was from Voyager perspective. There is the Saturn dot, again several pixels across. Here is a Voyager image as Voyager, and this is somewhere between these two, I guess, is a reasonable color. Here's a high-speed jet stream of the sort that I've been discussing, storm systems, which we discovered in the atmosphere of Saturn. Next, of course, is Uranus, another small speck in the sky as seen by Voyager, and there, of course, is how Voyager viewed it in false color back in 1986. And finally, Neptune, this small dot, just recently, less than a year ago, looked like this to Voyager 2. That's the small dark spot, the cloud in the center of the small dark spot. And the Triton and Neptune crescents. So this was Voyager's last light. And I think Carl would like to make some comments about this picture of the solar system. Carl?
So I'd just like to make a few remarks to set the context of this extraordinary mosaic. The first successful interplanetary mission of the human species was the Mariner 2 NASA spacecraft, which flew by Venus in 1962. The Voyager 2 flyby of Neptune occurred last year, that is 1989. In those 27 years, the human species has flown close by or orbited or landed on every one of the planets in the solar system with the sole exception of the planet Pluto. We humans have completed the preliminary reconnaissance of the solar system. There's only one time in history when this happens, when for the first time humans send their artifacts and themselves off the Earth and explore their local neighborhood in space. It's our great privilege to be alive at that first moment when ignorance is converted into knowledge. And speaking personally, it's an extraordinary experience to have participated in that preliminary reconnaissance. There are now 4 spacecraft which are beyond the orbit of Neptune and Pluto, Pioneers 10 and 11, Voyagers 1 and 2, heading out from the planetary part of the solar system. Shortly, we hope to penetrate the heliopause and enter interstellar space. And that also is an extraordinary accomplishment if you just step back and think about it. 4 vehicles of our species plummeting into the interstellar dark. Now, of all those worlds, including the 56 moons that the 2 Voyagers explored that Dr. Stone mentioned, we have no indication of life. There are the stirrings and intimations, if you like, on places like Triton and especially Titan, where it's very clear that complex organic molecules are being formed, but there is no evidence, not a smidgen of evidence, suggesting life anywhere else. And for me, that underscores the rarity and preciousness of the Earth and the life upon it. The portrait of the planets that has now been taken is, it seems to me, in the same tradition as the extraordinary color photographs of the whole Earth taken by the Apollo astronauts on their way to the moon, which for the first time gave everyone a sense of the Earth as a small blue and white world set in the velvet blackness of space. And for many people, it underlined the vulnerability and fragility of the Earth. It seems to me this portrait of the solar system has some similar feeling. And just to quickly restate, oh, thanks a lot. Here is the mosaic, taken, of course, in this odd shape because the planets move around the sun, and in any given moment they are arrayed about the sun. Next slide, please. Next slide. Thank you. And then here is a close-up of the outermost planets. Next slide. Here is the sun greatly burnt out in the Vidicon and Venus and the Earth. And the next slide. Right. The Earth in a sunbeam. And the next slide. This is actually the Earth. That previous one was Venus. And you can see it. This is, it looks like more than a dot, but it is in fact less than a pixel, a single picture element in size. In this color picture you can see that it is slightly blue, and this is where we live, on a blue dot. Astronomy has always been said to be a humbling experience, and I think these pictures underscore that point. And the next slide. Oh, no, it was lightning fast. Can we go back to that? That's it. So here are the 6 of the 9 planets imaged in this portrait. The 3 smallest planets, Mercury, Mars, and Pluto, we were unable to photograph. The appearance of the Earth in this pseudo sunbeam is just an accident. It was no special significance is to be attributed to a beam of light lighting it up. All, of course, are in reflected sunlight. Well, on that blue dot, that's where everyone you know and everyone you ever heard of and every human being who ever lived out their lives. It's a very small stage in a great cosmic arena. And again, just speaking for myself, I think this perspective underscores our responsibility to preserve and cherish that blue dot, the only home we have. Final remark I'd like to make is that there were many people who played a key role in making this picture possible. It was by no means easy to do, and I'd like to thank, among other people, Ed Stone, Norm Haynes, and Candy Hansen, all of whom are in this room, of JPL, and especially the NASA administrator, Admiral Truly, who played a significant role in making sure that this got done. Thank you.
Thank you. We're going to be opening the floor for questions in just a few moments. Just want to remind you, after the questions and answers are all completed, we will have a package of photos available for you and a video clip of the images you saw earlier. We have questions from the other NASA centers as well as headquarters, but we will be starting here. Ready? Are there any questions? Harry Rosenthal. Oh, please state your name and affiliation before asking a question, and please wait for the microphone.
I'm Harry Rosenthal, the Associated Press. Just to make sure that I'm not missing something, are we seeing a single image that includes all 8 of the planets, or are these 8 separate images that you put together?
The planet was imaged separately because they're too far apart to be in a single frame. So the wide-angle frames that I showed you, and which were on the last one of the slides that Carl showed, are the individual wide-angle frames, and inside of those we placed narrow-angle frames which actually produce the image of the planets themselves, and they're separate images. And so the 6 you see on the screen are the 6 of those separate images. Those are the 6 separate images.
Excuse me, may I follow up, please? Are the locations, though, are where the
Yes.
planets were at the time, at a given time?
As seen by Voyager 1 at that time, yes.
Yeah, I'm Dave Perlman from the San Francisco Chronicle. In the images you showed of the Great Red Spot and the smaller spots that were merging, do you have any kind of a model that suggests why one Great Red Spot is that great and constantly fed, and the smaller spots merge but don't make a larger red spot?
Well, that's certainly a good question, and I think I don't know that the model has been taken the next step, and that is to ask how much do you have to change the winds in order to either make more red spots or to lose the red spot you have. But it must have to do with the fact that the jet streams, which happen to be there at Jupiter at that latitude, are the right jet streams to create a great red spot. So then the question is, but why are those jet streams there? And of course, that is the next question which people are trying to address.
Bob Hager with NBC. Just for purposes of describing these 6 particular pictures, the release mentions 3.7 billion miles away when the shot was made. Is that a good figure to use for all 6 of those images?
No, that's how far the spacecraft was from the sun. Of course, it was much closer to Neptune, for instance, than it was to the Earth at that time. And I suspect we can get the numbers for you, but I think that one number probably refers to the distance of the spacecraft from the sun.
Is it possible to get the numbers? Because I think that'd be good when we show the picture.
I'm sure it's possible.
Mitch Waldrop, Science Magazine. Carl, you mentioned that this was very hard to do. What were the biggest technical and/or political and financial challenges to get this thing done?
Well, basically, you wouldn't want to take this before the science data taking with imaging was completed and calibration was completed. But at that point, because of the great strains on the NASA budget, you would want to free up the programmers and sequencers who have nothing else to do. So to take this picture at that point, you have to maintain the personnel past the planned for period, and that involves a substantial financial strain on a project which at that point is still running on a shoestring. Would you agree, Ed, that that's the...
Well, I think we wanted to take it after our encounters were over, and then there was this question of phasing it with respect to the phase down we have in the Voyager project as we move into the interstellar mission, which will be staffed by a much lower staffing level. I should point out that that there have been really 6 people who have been key in getting all this material ready for today, besides Candy Hansen, Charlie Avis at JPL, Randy Kirk and Larry Soderblom at USGS, and Eric DeYoung and Andy Ingersoll at Caltech. Without them leading the way, these images and the videos which I showed just would not have gotten produced by today.
Kathy Sawyer, The Washington Post. Not that there could be a dollar amount placed on the value of this portrait, but can you do that for us and tell us how much it costs extra to take this picture?
Yeah, of course you can't. I mean, nobody's kept detailed books, And rough order estimate would be it's probably around $200,000 or so. But that's a very rough estimate because nobody kept books on it. So we just don't manage the project that way.
Paul Hoverston, USA Today. Could both of you comment a little bit on your opinion of Voyager as a photographer? Is this about what you expected? Is it better than what you expected, or were you just happy to take whatever came up?
Well, remember that the manufacturer is guaranteed the product only as far as Saturn. There was no guarantee that as we got to Uranus and Neptune that anything would work. And in fact, both spacecraft have suffered from a variety of geriatric diseases. But what was most striking to me is that the JPL programmers and engineers got smart faster than the spacecraft got stupid. And as a result, on some level, the Uranus and Neptune pictures were better than the Jupiter and Saturn pictures. And remember, it's a region of the solar system where you're much further from the sun, so it's much darker, so you would want to take a time exposure longer, but you're flying by at such a great speed that you would be terribly smeared if you did that. And so you have to do a bunch of extremely difficult and clever tricks to get those pictures. So I think any one of the pictures, and certainly the whole ensemble of pictures at Uranus, Neptune, and the portrait that we just saw, are a great tribute to the JPL staffers.
Art Chives from Voice of America. Looking ahead to when Voyager gets to the heliopause, we don't know when it's going to happen, but do we know what to expect when we get there?
Well, we have some ideas, but of course, every time we've gotten someplace new, we found out that what we expected was not nearly as interesting as what actually was there. But I'll tell you what we expect, and nevertheless. That is that we will find that the interstellar medium, there is a much lower velocity wind. We have some idea how fast that wind is blowing, and we'll measure. We'll have some idea how strong that wind is once we find out where that boundary is. We'll have a direct measure of what the magnetic field is in interstellar space, rather than this magnetic field which is associated with the sun, part of the solar system. And we'll find cosmic ray particles out there which are excluded by the bubble itself. And so we'll likely find cosmic rays out there which we just are unaware of, in here shielded by the bubble.
How about how sharp a transition it will be?
I think there are some theoretical ideas about it. I suspect the heliopause itself may not be that abrupt and may be somewhat turbulent. Depends again on the nature of the interaction, and since something like this has never been observed before, I think all one can do is try to make the observation. It's probably not worth a lot of calculation in detail until then.
John Holloman from Cable News Network. Many of us in this room have been watching the Hubble Space Telescope, talking to the Hubble astronomers and the Hubble project scientists who say, well, now it's up there and we can start seeing some pictures. You guys have been seeing pictures for years and years and years. And this, as I think you said, Ed, is probably the last light picture. How are you feeling? How are you, Carl Sagan, feeling today at this point in this mission after all these years?
Great. It's been a wonderful journey. And I'd start it again if I had the chance. I mean, it's clear the right, how can one complain about such a mission? It's just wonderful. No, not at all. There's still exploration left to do, but it's clear the major part of the mission is now over.
But also remember that we have a huge number of pictures and other sorts of data that have been incompletely analyzed, some of them hardly looked at all. There are vast libraries of data which will occupy us, provided NASA funds such activities for a long time into the future. Excellent training ground for fledgling planetary scientists, excellent means of teaching science at all levels. It's not that we fly by Neptune and then everything's done. Voyager has long legs.
Earl Lane with Newsday. Do you have a best guess, Ed, on when one of the spacecraft might hit the heliopause and which one would do it first?
Well, the Voyager 1 is actually about 10 astronomical units further out than Voyager 2, so it more likely will reach it first. There are various estimates. My own guess is that it will be sometime after the turn of the century, perhaps between that and 2010. Before we reach the heliopause, we'll have our first measure of the size of the bubble, because the solar wind, I didn't point it out in the image, in the graphic, but the solar wind is supersonic and must become subsonic before it runs into the heliopause itself. And so the first indication that the wind is approaching the interstellar medium will be a transition from supersonic wind to a subsonic wind. There'll be possibly a shock, and that may well happen. That shock may well be observed before the year 2000 and will give us our first measure of the size of this bubble.
Okay, I understand we have a question from the Jet Propulsion Laboratory in Pasadena. Go ahead, JPL. Okay.
For Ed Stone, I presume that this is technically the last photograph that's even possible with Voyager. If, for some unlikely reason, you find something else out there you'd like to shoot, is it possible to reactivate the camera? And two, can somebody please explain why the Earth appears entrained in a ray of sunlight? What's the technical explanation for that?
Okay, your first question was what?
Can you take another picture?
Oh, no, yes. It's always in principle possible to take another image, but in fact, we are currently reprogramming the spacecraft for the interstellar mission, and once those new programs are put into effect on the spacecraft, which will be about August, at that point we will no longer have the capability in the computers on the spacecraft to use the imaging system any longer. So to take any additional images would require restoring that capability. In terms of the scattered light, it's just anyone who's tried to take a picture with the camera looking into the sun recognizes that you get a lot of scattered light, and this is just light being scattered off of the barrel of the telescope, if you like, which is the narrow-angle camera. So there's nothing intrinsically interesting. It's just the limitations of trying to take a picture looking at the sun.
And it's absolutely a coincidence, as I tried to mention, that the Earth happens to be in that sunbeam.
That's right.
Any more questions from JPL?
No more questions.
Okay. I think we have some questions from KSC.
This is Jim Banky of Florida Today. I have just two questions. First of all, how often will you take data from the Voyagers as you await discovering the heliopause? And the second question, for each of you personally, what was the most amazing discovery of the Voyager program? And what is the greatest mystery that is left unsolved, perhaps for Galileo and Ulysses and Magellan and whatnot?
First of all, in terms of tracking, we hope to be able to listen to the two Voyager spacecraft every day because, in fact, it's unpredictable as to exactly when there could be a big change in the interplanetary medium, in the wind blowing out from the sun. So we hope to continue receiving data, not 24 hours a day, but every day for as long as we can from each of the two spacecraft. In terms of the biggest surprise, I would guess, if I had to pick one, I would probably pick the volcanoes in Io, because in a certain sense that was such a dramatic discovery and really essentially forced us to recognize that we had to expect to see things that we were not going to be able to predict, and that from there on we had our eyes much wider open and had sort of took the blinders off in terms of the nature of the objects we would be seeing in the outer solar system. So I think that, if I had to pick one, would be the sort of the symbolic discovery which so characterized so much of what Voyager then went on to discover as it went further out in the solar system.
Well, I would also have picked the Io volcanoes, except for the fact that it was predicted just a week before in a paper in Science by celestial mechanicians who had calculated the heat dissipation from the tidal couple
They
of
didn't
degrees.
predict volcanoes, they predicted tidal heating.
They mentioned
They mentioned
the word
volcanoes.
volcano.
They mentioned volcanoes.
So for that reason, maybe the surprise was that they got it right, but from my point of view, it's very hard to pick a single most surprising item and a single greatest mystery. My list for both of those columns would have dozens of items on them.
Thank you. Now we'll have questions from the Johnson Space Center.
Stephen Govan, KTR KTV. A couple of questions. First, could you re-rack the I.O. video so that we could get it full screen back here in Houston? The second question is for Dr. Carl Sagan. The World Book Encyclopedia of 1975 contained a description of the solar system. What changes would there be in the World Book Encyclopedia description of 1990, 91?
We'll be replaying all the video that was shown today, as well as a new 5-minute clip that you didn't see that recaps the highlights of today's presentation. Okay.
On the writing of encyclopedia articles on the solar system, which I have myself done on occasion, you pick a very interesting date, 75, because that's before Viking lands on Mars and before Voyager gets launched. I would say you would simply tear up the article written. I don't mean this as a criticism of World Book, any article written before 1975 and start from scratch. For one thing, think of the number of objects that we now know are in the solar system that we didn't even know existed then. Then think of how many were mere points of light where we had no idea what the surface features or any details were. And then think of how wrong we were in our guesses about so many of the objects that we thought we knew something about. Voyager and Viking have wholly changed our knowledge of the solar system. Not, of course, the celestial mechanics of the planets. There are a few verities, but everything else is kind of prehistoric. The history of real knowledge of the solar system begins in that 1975 to 1989 period.
Okay, that's all from JSC. Are there any more here at headquarters? The back there. Again, please state your name and affiliation.
Bob Davis with the Wall Street Journal. I had two. First off, I probably missed this, but what happened to Mars on the pictures? And secondly, Mr. Sagan, you were talking about no evidence of life anywhere, but you talked about stirrings and intimations on Triton and Titan. I was wondering if you could elaborate on that. What do you mean by that?
First of all, as far as Mars is concerned, we realized that Mars would be very difficult to image because it would be overwhelmed by the scattered sunlight, these bright sunbeams, if you like, and indeed that was the case. We just could not pull it out of the very much brighter scattered solar light, so we just could not identify Mars.
On whatever I said, stirrings and intimations, I'm talking about pre-biological organic chemistry. In the early history of the Earth, some 4 billion years ago, there were sources of organic matter out of which life developed. The two sources are indigenous and exogenous. That is, organic material produced down here in the environment of the Earth, for example, from ultraviolet light or electrical discharges in a at least mildly reducing atmosphere. And exogenous, meaning organic matter falling on the Earth from the outside, which is mainly comets and asteroids. When we go to the outer solar system, we find in abundance both of those sources of organic matter, and it's true on all the Jovian planets. We think the dark materials on Triton are complex organic solids, but the most striking example, and Ed referred to it, is Titan, where the Voyager infrared spectrometer detected in the gas phase some 8 or 10 organic molecules, some of interesting complexity. Nitriles, for example, molecules containing a CN group, which are, we know from studies of the origin of life on Earth, are critical in the production of amino acids, the building blocks of proteins, and purines, the building, like adenine, the building blocks of the nucleic acids. In addition, Titan has this impenetrable orangish haze, which has a set of properties, so-called optical constants, determined by Voyager. And when we take the atmosphere of Titan, just nitrogen and methane, irradiate it with charged particles and or ultraviolet light, we make a solid particulate aerosol whose laboratory optical properties match bang on the optical properties of the haze of Titan. And when we ask what that stuff is made out of, it is a very entrancing mixture of organic molecules, including, if you hydrolyze it, essentially drop it in water, a wide variety of amino acids. So that's the sort of thing I was talking about.
Okay. There's two on that side.
Jacques Tiziou, French TV. Would you by any chance have a figure of the number of bits transmitted to Earth for the whole mosaic?
Well, the mosaic was 60 images total, 39 wide angles and 21 narrow angle images. Each image has in it 800 by 800 pixels, which is 640,000, isn't it, or something? And each pixel is 8 bits of data. Yeah. So it's 5 million bits per picture times the 60 pictures. Equivalent. Now, we didn't actually transmit that many because we've gotten smarter about using the spacecraft. So we transmit probably on the average 3 of every 8 bits. But I don't know exactly what we did on these images.
I had another one. What prevented you from downloading the pictures until March? Was it only Galileo and Magellan?
Yes, that's right. I mean, we needed the very largest antennas of the Deep Space Network, and we have other missions flying these days. And since this was not a time-critical activity, we fit in where it was convenient to fit in. So it took several months to get the images back. They were on the tape recorder.
Tom McChrystal, FrontierNet. Now that you've been through the major part of this whole journey, looking back at it, and if you were right at the beginning again, if you had it to do over, what would you do differently?
I really can't think of much that could be done. I mean, if you ask, what did we get compared to what we would have been happy getting, and we got hundreds of % more than we ever expected to get. So it's a question which, given the great success and the great return, it's hard to quibble about what we could have done differently. I mean, I think all of us are so pleased with how much more we got than we expected that we've never really seriously entertained, well, gee, we should have done this or should have done that. We were all so happy that we've gotten so many things.
The one place where I had second thoughts was delegating one of the Voyagers to take the Titan data, including the radio occultation data passing behind Titan, which then meant that that spacecraft couldn't go on to Uranus and Neptune. Seeing how tremendously interesting the Uranus and Neptune systems are, and the fact that there were objects there that we got nothing like the right data from, Nereid, for example, one of the moons of Neptune, I have in my mind gone back a number of times to think about whether that was the right decision, but seeing how extraordinary and important the Titan data are, I keep concluding we did the right thing. But I also keep missing Nereid and those other objects that we didn't actually see because we had only one spacecraft in the Uranus and Neptune systems.
Okay.
I think, of course, at the time we made the decision to do Titan rather than try to extend it to other objects, It was in the perspective of not knowing if either of these spacecraft would in fact live long enough to get to Uranus and Neptune. So there's a certain element of let's do what we know we can do rather than try for something we weren't sure we could do. Now in retrospect, both spacecraft are still working. So in retrospect, one can raise the issue much more easily than one could in 1980 when we had to make the decision.
Okay, next.
Greg Fryer, Computer Graphics World. Dr. Sagan, you mentioned that there's still a lot of data that still has to be processed, and also that you focused on an example, the Cray computers and the reconstructions that they were possible just in the last few years. Of the data that still has to be done, can we see some significant advances in our knowledge in the years ahead, and if so, how important would those impacts be?
It's always hard to predict what the results will be of data analysis that has not yet been performed. It's like saying, well, for Hubble, you know, what are the most exciting discoveries that you haven't thought about, that no one predicts is going to happen, that are likely to happen? And you know, by definition, it's impossible to give an answer to that. All I can say is that experience demonstrates that every time we take a closer look at the data, we find something very interesting. Take a look at the movies that Ed showed today, taken from data that we had 10 years ago. It's a very substantial improvement, in part because the image processing technology has made advances. That's another reason why the data aren't stale. Even if we've done everything we can with a certain set of data, the analytic and processing technology keeps advancing, and so we can dig more out of it.
One more in the back there.
Yes, this is A.R. Hogan, Writers Plus. Two questions for Dr. Sagan, please. One, if you had your wish list of all the types of projects that you possibly could want approved, notice we've neglected, say, a Mercury orbiter, a lunar polar orbiter, things like that. How many projects could you maybe tick off a quick list of projects besides the few stretched out ones that have been approved, as great as they are, if you could do that? And the second question, you said in a recent radio interview that NASA doesn't get the comparative planetology message out. Even NASA itself doesn't get the comparative planetology message out. With the increased interest in environmental issues, maybe this would be a good way to boost public support for planetary exploration. What can NASA and what can other people do to get that message across the public more clearly, please?
Well, on the question of what missions that are not now in the pipeline ought to be done, you'll recognize that different scientists have different items on their wish list. My wish list would include missions to Earth-crossing asteroids, that is, asteroids that come close to the Earth and, in fact, on occasion, hit it. I'd like to see landers on one or more of the Galilean satellites. I'd like to see rover and sample return missions from Mars. But most of all, if the United States can afford it, and if it can't, let's do it with other nations, I'd like to see a long-term commitment towards human flights to Mars. On the comparative planetology issue, my argument has been that the Venus greenhouse effect helps illuminate the terrestrial greenhouse effect, that the antiseptic nature of the Martian surface, due to the absence of an ozone layer on Mars, is relevant to us who are putting up CFCs and other chemicals that debilitate our own ozone layer, and so on. That these are real world, although extraterrestrial, examples which are very useful elements in the ongoing policy debates, and that NASA ought to be more vigorous in pointing out what we can learn from studying other planets that's relevant to preserving this one.
Thank you. This concludes our briefing.